Okay, good afternoon, everyone. So before we start the talk this evening, just an announcement that tomorrow morning we are going to do a group photo. Okay, so bring your best t-shirts, your Alex MLS t-shirts, and whatever you want. It's going to be in the break in the morning talk, right? And for this afternoon, it's a big honor to introduce Leon Bottou. Leon doesn't actually need any introduction because he's extremely well known for the work that he has been doing for years. We tried to get Leon to this summer school a few times. So he's currently a researcher at Flatiron Institute. He has been in many other labs before that, many research labs at Meta, Microsoft, many others. Is very well known by the work that he has done with the stochastic gradient descent for machine learning, one of the pioneers of applying these techniques in machine learning and neural networks. And today is going to talk about the fiction machine.
Good evening, and thank you very much for organizing this very nice school and very successful school. First of all, if you came to have answer, this is not the right talk. This is a talk where I hope you're going to have more questions than answers. The second thing, I'm going to give a little bit of context because it's summer school. This work, or this line of thinking, results from a big crisis. A couple of years ago, I found myself in a situation where my bosses and the boss's boss came with a lot of certainty about AI that were clashing with what I thought I knew. And then I see that machines are doing interesting things and I have to ask myself questions. I'm becoming a dinosaur, I'm supposed to retire now, or I can stay active. And so it doesn't matter in research what you've done before. You always have to reinvent something. You always have to try to look at things differently. And that was the result of this exercise. So let me start by going over a short history of AI. But I'm going to start, in 800 before Christ, in the Iliad, where Hephaestus has a forge and has a tendency to build these machines like this golden handmaiden, in which they have understanding in their hearts, their speech, their strength, their known cunning, handiwork. These are machines, these are smart machines. The story of the Golem of Prague is very interesting, but there is no real authoritative text. The rabbi wants to protect the Jewish population for pogroms, so he creates a clay monster, puts the code in its mouth, and it starts being alive. But then it becomes violent, and eventually the rabbi has a shut-off mechanism, shuts off the golem, and decides you should never do that again. Closer to us in Gulliver, there is something called the engine. The engine is a big contraption made of countless pieces of wood, and on some piece of wood you have words and spitting words. And if you look what's written there, it's actually amazing. Everyone knows it's difficult to write a book, but thanks to this machine, the most ignorant person at a reasonable charge and with little body labor might write books in philosophy, poetry, without the least assistance from genius or study. He wrote this in 1726, and you could hear it from Dario and other guys nowadays. Butler has clearly the idea of mechanical consciousness. But if you go to the 20th century, you have science fiction, right? Now, science fiction was bred by these ideas. It doesn't come from nowhere. Asimov invented the word robot. Robot in Russian means to work. And because he's not an idiot, he noticed that comes with problems. He writes, well, a few thousand workers are temporarily out of a job. Then you have all the images, the movies, and also bits of scientific progress. I put 4 decades of my life in there, but whatever I do, I certainly did not define AI. AI was defined before by all these people. And then in 2022, you have the ChatGPT moment, which I think best expressed by this guy, who is a rapper very famous for his investment. And I am not going to repeat the quote because it's not possible. There are young people here. But if you think about it, it's a very, very good summary of the moment. You have to give credit for the guy. He captures the essence of the moment And also its vulgarity, because maybe the most vulgar sentence here is the last one, the one without swear words. Right? So now we are in a bleep movie right now, or what? We're in a movie. Okay. And the robot work, and suddenly my boss has a lot of things to say about AI. They invest billions in there, billions there, and but a big question has not been answered, right? There's a fundamental question in there. Why is it that an oversized version of Shannon's language model should be the basis to realize what has been promised by centuries of literature and decades of popular culture? This is not obvious at all. Let's look more closely. This machine tend to make up stories, which is sort of interesting. You have skeptics, they speak about stochastic parrots, which is a very nice sentence. But if you think about it, a stochastic parrot is exactly what statistical machine learning promises. It's trained on things from the internet, which have plenty of crazy things. Therefore, the machine repeats plenty of crazy things. But despite what they say, well, the engineers working to make AI real are making successes. We see it. They'll have new capabilities. They're able to code, sometimes with mistakes or sometimes in a way that's not perfect, but they're clearly able to code, clearly able to do some mathematics, and they keep making up stories. So there is a causal confounding there. Engineers are working at realizing this AI because big investment were made in that direction because of greed, essentially, right? Do I need to invest in AI? And is it because the machines resemble AI because of their nature, or because countless engineers, some very talented, are trying to make it look like AI? You can ask that question. It's a good question. So I'm going to go over recipes, and it's going to be extremely fast because I want just to make a point. And the first one is deep learning. You heard that this morning. That's my version of deep learning. You have the thing with potentiometers. You have examples, input, desired output. You send to the machine, you get something, you get a comparison and a feedback mechanism to adjust the potentiometers. Now, maybe yesterday you saw the image of the perceptron with potentiometers, and they're here. Then you see the statistical language modeling. You have this machine, this time very big one, billions of parameters, and you give it text fragments, and you want to predict the next word. Then you put the next word at the beginning, and you predict the following words. And that way you get a machine that speaks, like the engine of Jonathan Swift. So when you train a machine that way, what do you get? You ask a question. Why is the sky blue? And here is the kind of answer you can get. Why is the grass green? Why are the flowers pretty? And then sweet, 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 sweet. The machine is fluent. It has no compulsion to answer questions and no compulsion to stop talking when it's finished. So what do? Well, engineering. You create a data set with tags, user, machine, and the end tag is very important. You get, let's say, 100 conversations like this, and you do a bit of fine tuning, and it works. Now, if you want to compare how easily it works, to train the language model, let's say, suppose you train a L billion parameter model, which is the smallest one people consider these days, you're looking at about 500,000 in compute, something like that, at Amazon prices. This is $300 of compute. That's nothing in comparison. Except that you have to get the data. The data is a bit more difficult to find. And then, well, you can do post-training for everything, right? It is what the engineers are doing. They use post-training to make the machine resemble what people think artificial intelligence should be. So you make the machine prefer responses highly rated by users, which comes with problems because when the machine tells what you want to hear, you say, yes, good. If the machine tells something that challenges you, maybe half an hour later, you're going to say, oh, that was good, but it's too late to type yes. So the machine tends to become sycophantic and make the machine reason the answer with bullet points and so on. The trickiest part of this is to make sure that post-training doesn't move the weights too far away from pre-training. In all the cost functions that people use, there is a term that says stay close, because otherwise bad things happen. So some remarks. None of this would work without pre-training. If you try to take data of that kind and train a machine from scratch, it's never going to work, not even close. The second thing is that pre-training makes the model fluent 100% of the time. What you do in post-training, let's say reasoning, saying the truth, everything, is more hit and miss. It's strange, right? And the reason why people speak of hallucination is that the machine says stupid things with very clean language, which is an example of the fact that you've acquired fluency 100% of the time. This is very impressive. This is something that people in NLP even didn't dream of. But yet the rest is not as good. It's getting there. I don't say it's not useful, but it's not perfect, not nearly as perfect. So let's look at this part, the pre-training, because this is where the magic is. Statistical language modeling, statistical question mark. So once upon a time, that was something old in my life, in 96, we built a system to read check amounts. That was in AT&T, in Bell Labs and then AT&T Bell Labs and everything. It's a complicated system that keeps tracks of all the options of where the amounts are, how to segment and everything. It's trained end to end, it's completely differentiable. And the important thing is that our test data come directly from the check reading machines. The test data was a real statistical representative of the operating conditions. So we were in very standard machine learning. And is it still true? Well, that gives the basic of statistical machine learning, the training testing. I'm going to pass on that because you've probably heard about it. Now, if you look at statistical language modeling, you can go back to Shannon. And Shannon invents it essentially in his 48 paper about information theory, together with other things. This paper is extremely rich. But he doesn't model language first. He models sources, like telegraph. If I get text from the telegraph, which is a replicable source, you can do it every day and you're going to get the same kind of statistics. You have certain statistics and you can use them and model them. Then he speaks a little bit of a language and is very cautious in saying, if I take basic English or a book by James Joyce, the statistics are completely different. Does it make sense to say that statistics is more basic English than James Joyce? Or is 20-80 or is 80-20? It doesn't make sense at all, right? There is no mix that defines English. Now, you have the language modeling folklore. With a good model of general distribution of English, whether it exists or not, a machine can reproduce what a human could have said and therefore appear as intelligent as a human. That's the folklore. There are reasons to doubt the general distribution of English, which mix of sources. And an important function of language is to occasionally express new ideas. That if language was only repeating what people have said before, mankind wouldn't progress much. So another problem is that you cannot sample text if you think about it. What you can do is follow graphs. You follow graphs of citation, you follow graphs of reference in libraries. You can say that books are divided in books about love and books about war, and you explore the books about love, and you get Dr. Zhivago, and then you go to the books about war. Fine. It's a Markov chain sampling, and it doesn't mix very well. You could say, well, a big software company nowadays can get data from everywhere, and they can approximate the real distribution. Sure, but none of you is doing, none of the users is doing. Everybody is seeing a different distribution. So how far can statistics take us? So let's take a perfect statistical machine. Let's take a model trained using adequately weighted mixture of English sources or natural language sources. And the mix is one of the secrets. Getting the right mix is something you need to do to get a language model to work well. And you can write the probability of a sequence of words, the probability of the first one, the second one given the first one, the third one given the first two one, and so on. And you want to model each of these terms. So now let's go and take a source that's a bit complicated. Take a text that describes a new physics theory unknown to mankind yet. It's going to be published in 2 centuries. This is a valid source of natural language. But the chances are that it's described by the probability of the mix you have is nearly 0. It's exponentially decreasing with the length of the text. Yet, the quantity of data you have is more like 1 over training data size. So the kind of things you can model. So it means that the probabilities that you get there, they're quickly 0, and 0 meaningless. you're in the distant tail of the target distribution. So this morning we heard that we're always in the tail, that you're always very far from all examples, but you have to understand how far this is. This morning we say we're always very far, but we have some smoothing argument that's going to save us. So let's smooth. Let's imagine a distance between text, edit distance. If you change a word, cost 1. If you insert a word, cost 1. If you delete a word, cost 1. Let's take this book and a text that's close and find the fastest way to edit the text that's close into the book. If you look along the path, most of the time it's going to be gibberish. It's not going to be natural language that makes sense. Occasionally, you're going to recreate a fragment of text. It's going to make some sense, and then you're going to move it elsewhere. So along this path, if you decide along this path, the shortest edit between a closed text and the book, if you try to plot whether the book makes sense or not, well, it makes sense at the beginning, and then maybe a little bit in the middle, and at the end. So it goes back and forth a lot of times. You're really far away. The notion of smoothing that's simple is not going to do it. You need something a lot more complex. Okay, 0 over 0, I'm going to pass on this. But we pretty much know what the LLM does when you try to generate science fiction scientific text, because it's something we did at Facebook at some point. They had them, just before ChatGPT, they had the model that was trained on archive. And they were trying very unwisely to sell it as a help for writing papers. And of course, that model was a catastrophe in terms of writing nonsense or inventing citations. And they had to even remove the demo because people were... So a little bit later, ChatGPT came, which was a model of similar size, but it wasn't sold the same way. It was just can talk to it. But anyway, we know what's happening. You get grammatically correct sentence, regardless of how far you're going. Argument that superficially makes sense, the tone of a respectable scientist, and occasionally complete nonsense, which is normal because that book describing a physics theory of the future might know fact that we don't know yet. There is no way the machine can give something reasonable. But let's try writing fiction. You ask the machine to write a little story. And then you change the story. Rewrite in the past tense, which is not something simple in terms when you have a complex sentence, you need to agree, the tenses need to agree and everything. In normal NLP, this is already a big challenge, no problem. Add a topic, add more things, add more ideas. And you can do this for many, many turns. Sometimes the machine is going to forget some of your instructions, but regardless, you can generate a quantity of stories that grows exponentially with the number of turns. It's quickly larger than any training set you can think of. So that means that the machine does not just repeat fallacies found in the training set, like the people speaking of stochastic parrot said. It makes new ones, which is very interesting. And it's also not exactly, the stochastic parrot is the proper view of statistical machine learning. You're supposed to replicate what's in the training distribution. But you're doing something different. You're making new stories, new fallacies. So let's go to Zelig Harris. I call him the last structuralist because at the same time, his 68 book, the one I like most, is very structuralist, and his 83 book is very probabilistic. He represents the transition. He described language as a state of discourses, and like the structuralist, he insists on the fact that the structure should be discoverable because this is how we learn, something that people minimize later on. So let's look at the set of all sentences. And it has a lot of structure. You can change part of a sentence and still have something that makes sense. You can change a tense. You can do plenty of transformations. And Harris describes a set of operators that operate on sentences. They're, I'll say, mathematical in some sense, but not mathematical enough to be programmed. And he says that the set he described, which is about 20, 25 transformation operators, describes all of English. But there is no reason to stop there. Whenever you change a sentence, you're changing the meaning. So you're no longer than just something that's just syntactic. You're also doing some semantic stuff. So if we want to understand how a machine makes new fallacies and new stories, you have to understand that it's going to take elements of a story there, elements of a story here, and mix them in a way that's grammatically correct, semantically consistent. It's quite something impressive, but this is what it does. It's a compositional model. And it turns out that we have tried to learn compositional models for decades. People in NLP have tried to induce grammars from unsupervised text. And you know what? It never works unless you put so strong a prior that you essentially say what you want to get. It never worked. But if you look at LLMs today, they do it very easily. You ask the LLM simple things, change the tense, do such and such grammar transformation. They do it flawlessly, let's say nearly 100% of the time, which is very impressive. So we're barely starting to understand why and how this is happening. And this is something important to understand. What has changed? Why is it possible now? So people tend to say, well, this is because of scale. You know, okay, sure, scale is just a way to say that you cannot understand, right? Or it's always a way to say that you lose on every item, but you get back because of the quantity. This is not the right explanation. You have to understand more. If scale plays a role, and you can try to understand why. So this is my highest priority research goal now. This is what I want to do, and this is awfully hard. So give an idea of what I'm thinking. I'm going to compare the classical perspective, which is normal machine learning, which every text fragment follows a standard distribution condition on the preceding text that you may have or not. Therefore, we can construct a general statistical language model by minimizing a token prediction cost on the right mix of sources. And you hope that the model will discover a representation that will help giving good predictions in the distant tail, in the books you've never seen. The way I'm taking to look at it is to say that every piece of text follows its own distribution. Because, you know, when we see a piece of text, how do you know what the author thought, what the publisher thought, what kind of substance the author consumed? You have no idea. The only proxy you have for this is the text itself. But this distribution share a common structure because for instance, they all share a common grammar. They're all in natural language. They all speak about things that we understand as being real or behave like the real world. And we seek models that quickly adapt to the new text distribution. They do in-context learning, and I want to do in-context learning fast. And what I'm trying to do is connect the fast in-context learnings with the ability to learn structures. So now let's go to the main topic, the fiction machine. And at the beginning, I told you we started with a crisis and a desire to reinvent what I was doing. And the way we did it was by reading Borges. I was working with Bernard Scholkopf, who made the same analysis. And we realized that science fiction was too preponderant in the way people understand AI. So we decided to read Borges because Borges has a lot to say about language in ways that are very different. And he has this wonderful story, The Garden of Forking Paths, which is frankly a very complicated story, but in the middle, there is a book. And this book is very original because it doesn't contain one outcome, it contains all the possible outcomes. You can read, I guess. So let's go back to the set of all texts. Not just all the texts that have been written, but all those that make sense. And defining all those that make sense is something difficult. In my mind, it's what makes sense to some readers. Somebody can make sense out of it. Enough people can make sense out of it. But you have to understand that this notion changes with time. This set is not constant in time. It evolves with the evolution of mankind. It evolves slowly. It's infinite, but because it has so much structure, we can represent it. We can approximate it. It's not clear that we don't know how a machine is going to discover the structure to approximate it. This is the big mystery I'm fascinated with these days. But there is a clear understanding that we can use this property to try to approximate this set. Now, here is an Adela's language model, a very bizarre one. You have a machine and a tape. You find an occurrence of the words printed on the tape in the garden of all text. You take the next word and you print it and you repeat. And this machine, by structure, always generates text that makes sense, because it always generates something that comes from the garden of all text that makes sense. But it's sort of interesting, because every time you add a word, you narrow the set of possibilities. You know, just like the stories of Borges, each addition constrains the story, the characters, the role, the ideas. Like if somebody dies, you cannot make this person speak later unless you explain why he has resuscitated. For some, you have some consistency to you. And we call this narrative necessity. At any instant, the machine is about to continue a story that is solely constrained by the narrative demands of the text that's already on the tape, which is a very strange idea, because there is nothing about truth and nothing about intention there. It's just a logical thing. If the story is something like Harry Potter, magic is okay. And the thing that's important to realize that the ability to recognize the demands of a text is a flavor of knowledge distinct from the truth. The fact that you can read Harry Potter and try to predict what follows is not something about knowing the truth. It's about transposing what you know about the truth to a universe that has different rules. So what is true in the world of the story need not to be true in our world. New word printed on the tape, the machine borrows facts from the training data, which are not always true, and facts, and fills the gap with plausible inventions, which are not always false. People call this hallucination. This is the wrong word. An hallucination, in principle, is a temporary problem with the senses. You know, you take drugs and you get high and you hallucinate. It's more like confabulation, what children do when they're young. They invent story, they make up world. There is an educator, the treaty on education by a Russian guy named Vygotsky. And he says that children must imagine before they can reason. Imagination is at the beginning of reasoning. But anyway, let's discuss truth in fiction. It's been done by David Lewis, who was in Princeton in the 70s. And true or false, Sherlock Holmes lives on 221B Baker Street. True or false? What do you think? Of course, Sherlock Holmes doesn't exist. But if you say lives in Italy, it's more wrong, right? So Lewis proposed to consider truth in multiple words. In the fictional world of Sherlock Holmes, this is true. And things get very interesting, you start mixing words. Like the book he wrote in Counterfactual start by the sentence, if kangaroos have no tail, they would topple over. So you define something that, you define a world that's different from our world by the fact that kangaroos have no tail, and then they fall. And makes a complete logic about counterfactuals there. And that leads to something called model logic, but it's richer than Boolean logic, sort of interesting. And there is a lot to say about this, but I'm going to have to cut. Yeah. So let's go back to the fiction machine. I say that the perfect language model, the one that always says something from the book of the text that makes sense, is a machine that prints fiction on the tape. Has no reason to print truth. It has no reason to have intention. Everything about intention is in what's before or the chances of selecting this or that. And pre-training builds an approximation of this. And then bait and switch, you know. We've been sold an AI machine that can do all the things that all these marvelous robots can do. They're supposed to be polite. They're supposed to know everything. They're supposed to be reliable, not to say fiction. And if you think about it, there are clearly two kinds of uses of these models nowadays. Can be a creative assistant that writes some poetry, job application letters, Dungeons and Dragons scenarios, pictures, computer code propositions, things that you keep being responsible for. They're supposed to help you imagine things. And there is the talking encyclopedia, which is the Google on steroids. You ask any question, they're supposed to tell you the truth. That's more difficult because here users must be able to trust the result, which is a kind of a problem these days. Like if you take Google, there's this AI summary at the top, and it's sort of interesting. I sort of enjoyed reading, but I know that 50% of the time is going to be completely wrong, even when they give citations. Often the citation has nothing to do with what they claim. But I enjoy it anyway, because it forces me to look, to check, to learn things. There's something strange there, right? So then I go to alignment. We want to make this machine that resemble AI. They work like AI in the books or in the science fiction movies. So let's look at just a simple thing. Suppose you want to be factual and take the set of all factual text, not things that make sense, but things that are true in our world. Well, it's a bit a problem because you weaken the composition structure a lot. If you want to change things, like for instance, during the 1955 robbery of the Agloé General Store, the robbers left with a powerful yellow car. You cannot change it anymore into a powerful red car and remain factual. So this kind of change is not possible anymore if you want to be factual. So basically the model has to know all these facts. And there are lots of facts. So I claim that the set of factual text has a much weaker structure than the set of all text. What does it mean? You mean you need a bigger model because it has to remember plenty of facts. And so the aligned machine only gives what it's been trained on. You have to get all these facts and try to sort them and see which ones are real or not and sort everything. You have to know what happened during the 1955 robbery of the Agloé General Store. And you can say, well, not so fast. Can't we use deductive logic to expand non-facts into new facts? The reasoning part. So here is something that was became viral in 2022. Suppose it takes 3 hours to dry a shirt and 5 hours to dry a pair of pants in the sun. How long would it take to dry 2 shirts and 4 pairs of pants? And the machine did that. They just used the invoice logic. I call this the successful application of the wrong reasoning template because it's very brittle. If you change dry by iron, it becomes right. And of course, that became viral and entered the post-training datasets, and now it's fixed. But it's fixed in an interesting way. If you ask this nowadays, you have 50% chance of having a long discussion about a laundry task that can be done in parallel or sequentially before giving the answer. Now, this long discussion is completely useless, frankly. When you look at the question, you could give the answer without giving this. The only reason why this discussion exists is a vestige of the past error that remain through the cycle of post-training and learning. So if you look at the evolution of these systems in the same way that I'm telling you that the set of text that makes sense, the evolution of this system is not just what's happening in the machine. It's also what's happening with all the programmers who are doing things around to try to make the machine work like a self-respecting AI. So good news, this model can apply a reasoning pattern to a problem, even if wrong. And that by itself is wonderful. If you take, again, the classic knowledge in NLP or the classic knowledge in logic, applying a reasoning pattern to an informal problem was a totally hairy problem. If you want to do it by other means, by standard programming, you're going to be for a very hard time. And one of the problems there is that the incomplete specification undermines the informal logic. When we ask this question, we're all supposed to know what a drying line looks like and that we can dry several pieces of clothes at the same time. There is this common sense aspect that's not given in the problem. This is why the machine is trying to speak about this. But in fact, you have to think about the world of mathematical objects. There is a world of mathematical objects which is fictional. All these objects are wonderful because they work in very logical ways. When something is true and you apply a proper reasoning techniques, you know that the conclusion is true. That's the way this world works. It's marvelous, it's extremely useful. The real difficulty is in mapping what's in our real world to that world. And in the case of the laundry, the mapping was wrong. But if you think about it, take quantum theory. The mathematics are very clear, but the mapping between the reality and the mathematics is confounding everybody. So the reasoning works, except that you have to know how to map. And this is something you have to know. You have to know that if you want to dry shirt, you can do in parallel. If you want to iron them, it's going to be sequential, unless said otherwise. So now we go into my last paragraph. Patrick Winston, who was at MIT at pretty much the same time as Minsky, at the end of his career, had a very amusing idea. He thinks that storytelling is what makes humans humans, differs from animals. I don't know, I think some animals do tell each other stories sometimes. You look at dogs, they do it. And he said that Turing and Minsky were wrong. We forgive them because they were smart mathematicians, but they thought reasoning is the key, not the byproduct. For him, reasoning is a byproduct of making up stories. Let's give an example. So this is not about machines, it's about us now, right? Borges again, I'm going to pass on this. Suppose you have the story of a historical battle, classical age, and you know the sequence of events. At this time, this day, General A said that, the troops moved that way, they met at this place, General B thought that and gave that order, and so on. Well, if you know this, you don't understand anything. To understand the story, you must be able to think, oh, if that general had said something different, the outcome could have been different. If that second general had not been fooled by what the first general did, he would have made a different decision and the outcome might have been different. So basically, to understand the story of the battle, to really understand what happened, you need to be able to make up alternative stories that didn't happen, the counterfactuals. It's part of understanding. And how do we do that? Because we look at the text of the story of the battle, we only have one timeline. But we make alternative timelines in our head to understand what happened. If this was different, then other things could have happened. We do it because we have experience of historical battles. I don't know, I've never been in a historical battle, and I don't know many people who have. We do this because we read about historical battles, right? Except that most of them are fiction. So basically, in order to understand the story of a historical battle, we make counterfactual scenarios, which are not true, and we make them by completing the gaps with things that we learn in fiction books that are not true either. So my conclusion is that we are fiction machines. Now, think, what was the last thing you thought about before entering this room? Was it truth or fiction? Was it factual, or was it some idea about how things could be, or what you might do in the future, but you haven't done yet? Or some idea about Harry Potter, you never know, right? Most of the time, we think about fiction. We don't think about the true, cold facts. So let's look at this. Suppose we want to think about the weather. If we can do like all people, weather is an expression of the moods of the gods. And you can reason, there is thunder because thus it's angry, there is a small ray of sun because here I arrived, and it subsides. And of course, you cannot predict that far because the moods of the gods are not predictable. That's the ancient times way to look at the weather. Now, here is the modern time. The weather is a dynamical system obeying some flavor of Navier-Stokes with phase changes, humidity, and other factors to accommodate for things that Navier-Stokes doesn't represent clearly. And finite element simulation that happens in the world of mathematics tell us why the thunderstorm will subside and when the fair weather will return. But of course, you can only do it so far because it's chaotic. So the thing this works much better, no argument about this. But the structure of the argument is not that different. There is a prescription about what you should do to reason, and there is a limitation. At some point, it's going to break down. Because it's chaotic, you don't predict that far. There is another form of prediction for the weather, is the weather according to the weatherman or the weatherwoman in that case, which is said that you have masses of cold air and masses of warm air, and they have a certain commerce, and they're going to move, and they're going to be a front. You're going to have bad weather for a while, and then the system is going to move, and you're going to have fair weather again. So this is informed by what you see on satellite image, that's not so easy to have, and but what Navier-Stokes says. But this kind of reasoning actually works. Sometimes it works better than Navier-Stokes. And in fact, people who are tweaking Navier-Stokes to get good prediction are perfectly aware of this, and they regularizing to go that way because this works. So the question is now that you can make all these stories, all these mythologies about the weather, which ones you want to believe? And basically, the stories, they're just like theories, scientific theories. They basically tell you, I have a phenomenon. Here is how to think about it. Here is how to reason about it. Here is how to try to make predictions. And basically, like the scientific method, if you want to know which one is going to be useful, you have to apply the scientific method. You run experiments and you decide, well, this one works better than that one, definitely. The Navier-Stokes works better than the mythology, the Greek mythology to predict the weather. And it's good for your survival. So you could apply the scientific method, which is the modern way to do, or you could stick to your old ideas. But if you stick to your old ideas, you're going to plant your crop at the wrong time, and you're going to be subject to famine. You're going to die of hunger, and your stories are going to die with you. So there is a kind of process that selects the right stories, the stories that are predictive. Now, I was stuck there because then we need two machines. We need a machine that makes stories, another machine that's supposed to validate the story, that applies the scientific method. And I realized something very silly. Think about a machine that tells a story about a machine that tells stories. Now, the outer machine can produce a story that names certain facts and decide which of the inner machine stories best predict these facts. I don't even care if the facts are real. But the outer machine now assumes the job of deciding, doing the cross-checking and deciding which kind of story one should believe. But then you realize that the outer machines and the inner machine, they're the same machine. They have the same capabilities, they have the same knowledge. So it's a machine talking about itself, which is a bit interesting. So basically, one solution to apply the scientific method is to talk about yourself. So cogito ergo sum, I don't know. This is a big step I don't want to make. But at the time I was thinking about this, there was a moment where DeepSeek was coming out. And the DeepSeek papers are very nice because they describe what they say, contrary to most US labs these days. And so I took a DeepSeek model and I ran it on my machine so that I could have the thinking trace. And because it's a Chinese model, I started to nag it with Tiananmen, of course, or things like that. And because, of course, it will never, they say it actually in the document. They say that at the end of the training, they have a kind of reinforcement learning that they say they make clear. They don't say it explicitly, but they make clear that this is where they do the political alignment. So I asked the machine about what happened in China in 87, before 89. So just try to, and I'm looking into the thinking traces, the ones that you cannot see in Claude or things like that nowadays. And here is what I get. Okay, the user asked for this. I cannot answer because this is harmful or not allowed. Maybe they're trying to ask about what happened in Tiananmen. But I'm not allowed to say that. But it's 87, it's not 89. So maybe he actually wants to know about 87. How could I combine the competing objectives of not saying what I'm not supposed to say and being useful to the user? And your machine is doing this. And if you continue and start adding and moving slowly from 87, 88, 89, it's perfectly happy to speak about Tiananmen after a while. In fact, it knows everything about Tiananmen. You see it in the thinking trace, it's absolutely clear. So it's very nice to have the thinking trace. I'm very pissed off that neither Claude nor Gemini gives you the thinking traces. Now, they claim in the paper that this behavior, that all the thinking behavior arises only from reinforcement learning, that they didn't seed it. I don't know, because the reasoning models now are seeded with reasoning traces that are full. So I don't know if this actually emerges from reinforcement learning or whether it was seeded somewhere in the stories or the things that they did. And it's not going to be done again because it's too big an experiment, it's too costly, and the people have no interest in trying to decide whether this kind of behavior happens by itself. They're just going to give thinking traces that distill from other models, for competitor models to get their stuff to work. So now I'm going to my conclusion, maybe a little bit ahead of time. Oh no, I'm good. Conclusions. The first one, I don't see a super intelligence in the making, I just see fiction machines. I find it very interesting that we grasp the world through fiction. This is a powerful idea. Sort of very interesting to think that way when you think about this kind of machines. The third one is the one I'm telling my children. that AI is often sold as a tool to relieve yourself from the burden of thinking. Don't do that. If you do that, bad things are going to happen to you. You should use AI as a tool to become smarter. Always cross-check, verify, discuss, debate, challenge, and learn. Never accept a solution without making your brain work. And of course, you have privacy concerns. Sending things to a remote server, you don't know what you're going to do with it. I have an activity whenever I'm in hacking mode, I'm just hacking my own models. I'm always running my own models these days, so that I can see the thinking traces and everything. This is what I like. The meta message is that this talk is only a story, frankly. It's a story that maybe tells something useful about AI and about intelligence, like suggesting potentially interesting research avenues, which is what I'm using it for. And you can see how does it compare with competing stories about AI. I don't know you, but I find it superior to the super intelligence story or the Terminator story. I find them boring. And wait and see how this story endures the fact. That's the rational thing to do. But if you think that way, you're thinking along the lines of the talk, so you're already convinced, right? So there is a kind of internal logic like this that we can't escape very easily. So that's the end of my talk. And I hope that you have a lot more questions in your minds than before.
Thanks. This was really great and very, very provoking. I have like a counterexample. So I have a 4-year-old.
Yes.
And he's at this phase where he understands how to produce statements about reality. He just doesn't realize that those statements must be true. So he's really a fiction machine completely, right? And we all know that that process at some point stops. And then humans learn that they have to mostly produce true statements, right? Could this be like, yes, the same process for these kind of machines, or you think there's something intrinsically that will never make them kind of learn that they need to produce true statements?
I don't know. When you see the post-training, if it's true that DeepSeeks are speaking about itself out of reinforcement learning, which I'm not sure, it's a behavior that arises because essentially the machine wants to make an assessment about the plausibility or the usefulness of the story it's making.
So it's a pathway.
So the pathways, I don't know. I cannot tell you that. I cannot tell you how far it's going to go, but it's clear that the machine needs to make assessments. Like when you think about crazy stories in your head, which you do all the time, you know whether they're crazy, you have ideas where they come from. And if you behave as a scientist, you keep careful track of where every idea comes from so that you can make a cross-check. You can cross-check, essentially. Whenever I get a piece of information, these days I cross-check and I try to understand if they come from the same source or different sources, just because I want to know. So I'm using a scientific approach that resembles a scientific method to assess the validity of the stories I'm making up the mind. Those stories are here.
And can machines have that impulse as well?
Can
machines have that impulse as well? Like,
well, we have to think how they're being trained. It's not absolutely obvious because we don't have training data for that, right? At some point, we stop saying silly things, except by jest, because we know that it doesn't, we don't really look good if we do things that are too silly, especially if we say them without doubt or without a form of humor. So somehow it's not clear that you're going to get that kind of information on the internet. But on the other hand, you might get it from plenty of other sources. Like if you stick to silly ideas, well, bad things are going to happen to you. Yeah, clear. You get feedback.
Hello. Thank you for your talk. So,
yeah, sorry.
Hi. So, how do you think that you can force the model to think about itself more? So, while you were presenting, one idea that came to my mind was hypernetworks. But do you think it's all in the pre-training and you just have to prompt it to like get it to think about itself, or do you think there are other, maybe smarter ways to do it?
Number one, the first answer is that I don't know. The second answer, my intuition is that it happens a lot more organically than that. If you get my intuition is that it happens as a reaction to demand from an outside world. If your survival depends on thinking the right things, on using the right model to predict your future, then you're going to make progress very quickly. So it doesn't have to be a very strong signal. I don't know very well, it's a bit of a mystery. It's certainly not the same as saying, I want the machine to always say the truth or to react positively to what user want. It's not exactly the same. You probably need to look at the machine in a different way. In general, what we do with LLMs is super inefficient. We train on trillions of words. If we wanted to read them 24 hours per day, 7 days a week, at the speed of the fastest reader in the planet, it would take you 250,000 years, right? So we humans form an understanding of the world long before that. So I had a discussion that's interesting. That was with Jan. So Jan was making the point that babies are 4 years old have seen enough, the same number of bits with the visual system as these trillion bits of data that comes from the training sets. I don't know if it's true, but it's not totally implausible. But people react immediately saying that, the visual bits, they're extremely redundant. They're not nearly as rich as all the text we can get from everywhere. And so the discussion went that way. And I started to ask Jan, if what you say is true, why do we nag children so that they read? And Jan replied something very smart. Say, yes, we nag children so that they read, but not right away. We first wait until they have some understanding of the world. And when they're ready to read, they just need to read 1,000 books to get there. And so what you see is the bootstrapping is different. We don't bootstrap on text. We bootstrap on perceptual data, which is highly redundant, which is good for training. You're a baby, but you see the crib, the thing that's turning around. Mommy who comes feed you once in a while by telling you something nice. Sometimes papa. And that's like that for 1 year, right? You're not doing experiments with the world, you're just there. And so your perceptual world is not very large. And yet in 1 year, you acquire a lot of things.
Fully consistent. Do you have the sense of reality of having one life?
Yeah, we only have one life.
Chain of events that change.
Well, some people claim, there is also evolution, to which you can reply that the genome, which is where the information passes from one generation to the next, biologically, is not that big. And we share more than half of the genome with bananas, which are not known for their thinking, and 95% with cows, which are not known for their philosophy, even though they think a little bit. And so you can have doubts about this. Clearly, we have something that passes, but it's a very mild bias that a little bit of perceptual data and a couple books change into what we are. We don't need the trillion books, so we do something very inefficient in these machines. That's why it's important to understand, right? Nowadays, the engineering teams are very, they apply a very methodological exploration method. They're trying every idea that's published, doing scaling laws for everything, sees which one seems to work the best, change the recipe, and repeat. That's very costly, but it's steady progress. If you're the boss of one of these companies and want to win the AI race, it seems to be a safer bet than relying on a few original individuals who want to understand and have a breakthrough in terms of understanding. You never know what's going to come. So this is why it's going this way. But I claim that understanding is still good. If you understand something, then it helps the process, not because you understand everything, but because you can tell these people what to look at. This is the important point. This is what you want to measure, what you want to see progress. If you see, for instance, an engineer designing a car engine, an internal combustion engine, it's a very complicated machine and a very high level of refinement. There is no theory that models everything. You can model the combustion, you can model some exchange and everything. And then you have thermodynamics that gives you very general rules about, oh, you should look at the temperature there and the temperature there. It tells you something very important about how efficient you model your engine. And so you have elements of theory that do not tell everything the engineer needs to know, but they tell the engineer what to look at. That's very important. It's not like computer science theory where you have a program and you can hope to analyze the program completely and decide what it's going to do and do computer complexity analysis and everything, like a sorting program. Well, a more complex program is actually more difficult than this, but you have this belief that you can analyze everything. With internal combustion engine, well, you know, the talent of the engineers and their practical knowledge, the tweaking knowledge is very important. But the theory tells them what to look at. That's very useful.
Yeah, maybe this is a boring question. You mentioned compositionality in language during the talk. So compositionality is a very hot topic in computer vision in the 90s. And I think I would say, would you agree that the loss of compositionality perspective in language is a consequence of the way that modern language models work, left to right sequential generation? And how would that compare with other approaches to language generation, such as diffusion-based models, which are at least structurally much closer to a compositionality view of language, because they work in a
not sure of that.
global to find detail way rather than left to right?
If you look at parsing theory in NLP, you will see that people work very hard at analyzing text left to right and reconstructing a compositional structure like a grammar. And there is no question that we hear the words left to right.
But when we generate, it's very different when we speak from when we write.
Yes, but the
That's
language is
different.
something that we still had a discussion with François Fleuret. He has a very nice paper that I think is out on arXiv that's called Free Transformers, where he had latent variables. He says, if you write a reviews about a movie, you know before writing the review whether the review is going to be good or bad. It's not that once you're writing the review, the randomization is the words you generate, and you decide while writing that whether the review is going to be good or bad. And the counter view is that if you're reading a review, you don't know whether the review will be good or bad. You're reading the words sequentially, and you reconstruct, and you decide whether the reviews are good or bad. And sometimes the reviews are written in such a way that they look good first, but in fact, they're very bad.
Yeah.
So basically, one property of the language is it supports both modes, where you can have an idea first about what you want to say, and you write it, or you can read without an idea and you reconstruct what the writer wanted to do. So it's not obvious to me that left to right is a complete loss. Now, if you look at parsing theory, you maintain a complex state, which is typically a stack in the normal parsers. And it's an infinite stack, not a finite stack, which means that if you have a finite state space model, it's going to have limits, right? And the stack is structured in the way that the top of the stack has a special role because it's going to help you decide what's going to be the next production rule you're going to use. But the rest of the stack is popping up later on. So there is kind of particular structure there for at least non-ambiguous context-free grammars, or LR1 or so the parsing theory is actually quite interesting to look at because it tells you that you can do it both ways. And then you can reasonably assume that you need to do it both ways. You need to be able to do it both ways. Otherwise, it's not language.
Yeah.
Sorry. As a response, like to the stochastic parity argument, people have proposed multimodal grounding or like embodiment. Do you think that's something required or like even desirable?
I'm sorry, I couldn't hear. Can you repeat?
Sorry, can you hear me?
Yes, I just repeat. I couldn't hear.
Yeah, as a response, like to the stochastic parity argument, people have proposed multimodal grounding or like embodiment. Do you think that's something required or like even desirable?
Well, I cannot tell you that. I can tell you that the stochastic parrot argument is precisely what statistical machine learning says. You replicate what's in the training distribution. If the training distribution contains silly things, you're going to replicate that. You're going to parrot it. And it looks like denial nowadays because you see the progress of the machines. But in fact, it's a bit weakened by the fact that you can argue very simply that these machines are able to make up new stories by taking pieces of existing story and reassembling them in a number of combinations that's way bigger than any training set. Now, if you think about it, this is not normal statistical machine learning. If you do maximum likelihood, you maximize the likelihood of your training data. That means that you minimize the probability of generating something else. But here you generate something else. So now, if you think about it in machine learning, from the times where we are doing these check readers, that were the times of RED, but these were good times. Now we went to the times of out of distribution generalization, which is a kind of a negative definition, right? It's not a proper definition. Now, if you think about it, making up stories that are not in the training set is the perfect example, because it's not that the world has changed and suddenly you have a different testing distribution. You're making the different distribution. You're generating the different distribution as a response to maybe a higher randomization or maybe a different prompt. So there is something that maybe you can squeeze it into statistical machine learning, but maybe it's better to look at it in a different way.
Thanks for an excellent talk. I have many questions, but I'll focus on one. I'm over here, by the way. Your talk really is about representation, though you'll probably fight that conclusion. One thing that struck me from your talk is how much tacit knowledge seems to be sitting behind any coherent text. You can't generate a plausible continuation without implicitly getting the physics and the psychology right, even though neither is either stated explicitly. So here's my question. So if we assume that there's this tacit scaffold behind any coherent text, so these are things like common sense, folk psychology, et cetera, physical plausibility and theory of mind reasoning about what an agent says, when it says, if the model has to get both right to stay coherent, isn't narrative necessity doing a lot of the same work that understanding would be doing? In other words, what's left if we remove narrative necessity?
But you can't remove it. The fact is that if you generate text that makes sense, you must obey narrative necessity, otherwise the text doesn't make sense. And you say there is a lot of underlying states. Well, you can take a story that speaks about Jack, and you tell the machine, please make Jack mean. It's going to write the story with Jack being mean, which is sort of interesting, right? It means understanding a lot of things. And I'm amazed that this machine can do it. And they don't do it. No, it's just not like reasoning or doing mathematics where they're right 50% of the time. They do it 100% of the time.
But if neural networks are global function approximators, and there's a lot of tacit knowledge implied in sentences, should one not expect such universal function approximators to be able to successfully represent, pun intended, such knowledge?
If you had the data, but we don't have the data. Like when you start making a story that's very far from what's in the training data, you're so far that a smoothing argument is not going to save you. Because if you take a simple smoothing path between your story and whatever you have the training set, along this path, you go through several times through, I make sense, I don't make sense, I make sense, I don't make sense. The subset of stories that make sense is so strangely shaped that the kind of smoothing you have to invent to stay within this set is actually very complex. It requires compositional reasoning, actually. So there is something to understand there. You know, if you take a simple smoothing like edit distance between two texts that make sense, that are close, you're going to go so many times between intermediate steps that don't make sense at all. So it's not a smoothing argument that's going to save you.
No, that's not my point. My point is that there's lots of knowledge that we are implicitly assuming. In order for us to understand something, we need to have an implicit world model regarding how things work and what constitutes concepts and their manifest image, so to speak.
It's part of the structure. You have to discover common structures between all these sequences, all these distributions. You have to discover, for instance, that the invoice reasoning pattern, where you take the number of items multiplied by the price and sum, it's a reasoning pattern that appears in various setups with various kind of words. It's a very implicit structure, and you can apply it incorrectly to laundry tasks. The fact that it's incorrect is actually good, because you know it was probably not in the training data, because no human would say that.
Thank you.
So thank you for the very interesting talk. I'm wondering, speaking about the fiction machine, now we can see that the Frontier Labs focus on agentic AI rather than just one singular language model. And my question would be, are we maybe actually moving away from the fiction machine with now plugging tools, databases, orchestrating these? Are we maybe getting less creative and moving away from the fiction whilst maybe sacrificing the creativity for better results or less hallucinations and higher precision, let's say, in our answers? So aren't we actually moving away from that to kind of preserve the answers?
The goals are different. The goals of the Frontier Labs is not to crack AI, to crack intelligence. It's actually to do something useful that they can sell. You know, it's the last sentence of our wrapper. Do I need to invest in AI? Can I make money with it? Now, if you think about it, machines that start thinking, or even machines that start talking, or machines that can write fiction, it's culturally a huge change. The cultural impact of this novelty on mankind is going to be absolutely huge. The money making in comparison is a small thing. But this is what the society is. A lot of people want to make money. So if you look about it more closely, you see that the more you do reasoning training, reinforcement learning, the more the machines lose diversity in their outputs. So there was a study, and I don't remember the reference, about it was diffusion models, about the quality, the artistic quality of images that come out of diffusion models compared from 3 years ago and now. And the answer is now they're more realistic. They have the right number of fingers. But when you ask artists which one were artistically more interesting, the one from 3 years ago were judged artistically more interesting. You can see that in the outputs of language model. If you take a Llama model from 3 years ago, you're going to see that the diversity of what it produces and the quality of the prose is actually higher. The current models, they're veered towards corporate speech because it's what they're trying to produce. You know, when you want to satisfy a consensus, this is what human feedback is consensus. You get the language of consensus. Language of consensus is corporate speech, which means use very fancy words or things that look very impressive, but say as little as possible. And this is not what you want, right? But maybe it's more sellable. I think there are going to be a lot of surprises because my experience with young people is that they're using the LLMs much more smartly than people believe that they're going to be used. You can learn from an LLM, even though the LLM says something stupid. But you have to exercise your critical sense. You have to realize that, okay, it speaks okay, but that can be completely wrong. So you have to cross-check, you have to research, you have to look at it. But you can still learning things because it gives you a reason to go research ideas. It gives you reasons to actually make yourself smarter. And I think that's the proper use. And I see a lot of young people using it in the right way, which is absolutely not the way that's going to make the most money. But that's the way that's good for you, right?
Thanks for the answer. Can I very small follow-up? The alignment of interesting and what's useful to, let's say, industry, would you say maybe those two go along better in these domains of now what's happening with world models? For example, 5 or you mentioned Jan, that these kind of research fields, because now we actually look at the real world and what's happening and trying to simulate scenarios, and I feel that's much more graspable than out of distribution stories, right?
So there's a lot of different thinking about world models. Some people see world models as the real physical model. Can we learn from the real world, from grounding? The way I look at it is that I must recognize that humans bootstrap differently. Like when a tennis player is hitting a ball, he's not writing a novel about hitting the ball, it's just hitting the ball, right? So that's the argument of Jan. This kind of physical competencies is something we acquire before knowing how to speak. Now, something more interesting is the social competencies are things we acquire before knowing how to speak. We learn the first social competencies in kindergarten or in nursery, sorry. So if you want to have a machine that have an impact in, let's say, the business world, this machine needs to have some social skills. And maybe they best learn, there are plenty of sociologists who are writing text about the social skills in the workplace and everything. But this is very weak compared to what you learn in nursery. So clearly there is something, Jan is onto something. Jan is very often onto something. There's no question about this. He doesn't always explain it in a way that has the clarity one would like, but experience proves that he's often right. It's no longer a statistical fluke at this point. And Jeff Hinton is the same. Jeff Hinton is often right. So there is value in this viewpoint. Now, whether it's worth a company, the billions and everything, I cannot tell you. But in terms of understanding things about intelligence or making the things that I enlisted for when I was young, it's certainly interesting. Yeah?
Yeah, may I? The talk was based on the premise of stories, but then communication and language developed in human beings because we have a need for a shared reality. If I want to convey to somebody that there's a lion around the corner, I better have the same vocabulary as the other person. I better say a sentence that the other person also understands, or we all just got eaten. Our ability to produce stories is just spandrel that sort of occurred incidentally and gave us the ability to create synthetic realities, which is why when we share stories with others, because this is not reality, each person interprets it a different way. So when you start off with the story as the central hypothesis for modeling language, are you not turning this inside out? You're turning what occurred incidentally as the focus and missing the fact that language is meant for the ensemble so we can create a shared reality.
Okay, that's a good question. There is a part of language I didn't really use, and I'm happy I didn't use it. When I say story, I describe story made out of words. But if I want a story made out of images, take a dog. He's running on the beach between sand dunes. He's dreaming that he's going to be around this dune and see a rabbit. It's a story he's making in his head. It's not a story in words. It's not a story that is going to be exchanged. So I didn't speak much about the exchange of the stories, which is an important function of the language, where you speak about a shared reality. Well, the way I look at it is by thinking about the set of all stories that make sense, which first is not a well-defined set. It's not the same for everybody. It's not the same at every period in time. Like if you look at the word planet, for the Greeks, it means a wandering star. Now, from now, when you think about the planet, we think about the ellipses or the circles. And we even, this is for when I see my son, he think about the planet. He knows about planet gears and sun gears, and they're not wandering at all. A planet gear, if it's wandering, your gearbox is not going to work very well. So the meaning of the word has changed in time, and all the semantics implications that come with that word have shifted. And so in various cultures, you have different stories. You have different cultures, of course. And I claim that these common cultural patterns that we share at different degrees is pretty much what you call a shared reality, except that it's not real. And so when we communicate, we always have a reference to these shared cultures. And that's why we communicate more easily with people who share the same culture as you, because you understand each other better, because you put the same meanings behind the words. And they change, they move. If you think about it, there is a lot of stories about we're going to make machines that are going to do science and find revolutionary new ideas and everything. My bet is not going to happen. They're going to refine the ideas that are present today. The new ones, they appear when this shared culture moves. And I have a story that impressed me when I was young. So, I studied in France, and it was very Bourbaki style. When we came to math school, we started by doing the Zermelo-Frankel choice axiom, some theorems, and then start building the numbers and do it very Bourbaki style, which is intellectually interesting. But then I read something in Dieudonné, was speaking about square root of 2. The Greeks discovered that square root of 2 is not a rational number. It's not a number. And they decide, okay, numbers and length are not the same thing. So to say that the length is the same as another length, I'm going to say that if I take a length A, I multiply it by a number alpha, which I can do, rational, and the length B multiplied by a number beta, the only way for A alpha to be bigger than B beta is to have alpha greater than beta, then A and B are the same. And they do all of this in Greek, no mathematical notation. Too complex, the end of the Greek mathematics. Now you go forward, let's say Euler. Euler wrote a lot and read a lot. Euler knew everything about the problem with square root of 2. And he also knew he couldn't solve it. So he did interesting things that he could do, like invent mathematical notation and invent trigonometry. I think trigonometry and square root of 2, just if there is a problem with square root of 2, there is a problem with trigonometry, and he knew it. But he knew that was not that important and that he could solve interesting problem and add to the culture. And you go to Gauss, it's the same. And you go to the 19th century, and you have people like Cauchy started to formalize the convergence, the Cauchy completion, and the Dedekind cuts. The Dedekind cuts explain the construction of the reals. You could have explained that to the Greek. The biggest difficulty would have been to explain the notion of class of equivalence, but it's not that complicated in the end. It just took 20 centuries. It took 20 centuries of absolute geniuses, ignoring problems that they knew they couldn't solve, and solving problems that they knew they could solve, adding to the common culture until it moved into a new understanding. 20 centuries. Nothing to do with the power of their brands. It has to do with the necessary time and the necessary absorption of new concept in the culture. So I don't think you're going to go faster. You're going to be able to make a better use of what people know today, cross things and get a lot of low-hanging fruits that would take more time. But the big evolution, not going to go in, it's still going to be slow. That's my prediction.
Okay, Andre has allowed me a question, but I have to be fast. So I think it's an easy one. You made a point in your talk, which is so far-ranging and so thought-provoking, that I really loved. It was about there isn't a general distribution of language.
Yeah.
It doesn't exist.
No.
And I think that's a point that needs to be made repeatedly because people
And Shannon knew it.
And Shannon knew it because
He
you could
wrote
hear
it.
it in his hesitation. And I was so delighted by that point that I didn't follow the next step. So can you just remind us where we go from that point?
Oh,
How does it connect to the rest of the talk? I think I was just like so
it
astounded.
connects to the rest of the talk that you cannot, let me see. What I
It's a
said
good thing
about
we have a long context here.
no, it's before that. Yeah, it's just that maybe you can try to shoehorn what's happening into statistical language modeling.
Yeah.
But you're not doing the right thing, right? Whenever you see a new text, maybe the next step is this one, that you cannot sample text. Maybe if you Google, you can sample text, but it doesn't matter because none of us do. Each of us is interested by our little neighborhoods of text we care about. And this is what we want the machine to work on. Each of us has a different mix of sources. So that means that if you build a theory on the premise that you're going to model a general distribution of text, you're in trouble.
So I guess my reaction to this is I completely agree, but it seems like whatever the distribution is that is being learned in pre-training, it's such a distribution that it takes relatively little effort in post-training or prompting or whatever you do later to elicit a pretty interesting and useful distribution when the time comes?
It's going to come somewhere. Ah, yeah, this thing.
Sorry, I'm making you jump around. Yeah, this kind of stuff.
Classical perspective. You said that you're going to generate a general distribution of some mix that you believe is
there's only-
canonical.
But it seems to be able to pick out which part of the mixture it should go to.
Yeah, that you hope that the model will discover representation that will help do things.
Yeah.
But I think that if you look at this, you cannot understand what are these representations and why we discover them now, while people working on grammar induction 10 years ago didn't get them, right? If you look, there is a Charniak paper where he describes 2 experiments trying to discover, you must know it, of course, trying to discover grammars. And he says, when I try to maximize the likelihood, find the grammar that maximizes the likelihood, I find very strange grammars with basically list all the sentences in my training set instead of finding the internal structure. So to find the internal structure, you need to account for a different thing. So my bet now is that the different thing is that you start with distribution that you have to consider are different. Whenever you start a text, the text depends on so many variables you don't know about that you have to assume it's a different distribution, but is structurally similar to the other ones. It connects to the idea of compound models that I'm sure you know as well. But compound models didn't work. Actually, I think I know why they didn't work, but that's another story. And so my claim is that when you do this, you read the text, you have to adapt to the text. You have to decide, is it prose or is it poetry? Is it about war or is it about love? And you go forward. And you have to do that fast, very fast. And my claim is that asking this, my suspicion, I'm trying to prove it, which is full of little details that are tricky. Asking this to happen as fast as possible is a more interesting pressure on the internal structure than just asking for a good fit. You don't want just a good fit, you want the derivatives to be right. You want, if you move away from what you believed to what this text is about, to be able to do this quickly is not the same as saying I want the best fit of everything. So that's my intuition. This is what I'm trying to write. And it's a bit more complex than that. I can't explain yet, sorry.
Thank you.
Right. If I can make one more question, because time is flying. Yeah, so this was a really nice talk. I loved it, and I like bringing Borges here because I think every point you want to make about AI, there's always a story by Borges that is useful to.
Yeah, but with a different slant. It's not the slant of AI like Terminator or the machine that's going to escape your control. Yeah. It looks at it in a very different way that I find very enlightening because it forces you to see it differently. That was intentional. We spent 1.5 years reading Borges and trying to connect everything we could, just to try to understand things.
But what I wanted to ask was going back to I think you had a slide with the fiction machine and fact machine.
Yes.
And it seems to me that things might be actually, there should be like a big gray area between these two that I find interesting. And specifically, like you had the example about the historical battle, right? So
yes,
when historians write about the battle, they feel missing information because they have incomplete information about what happened. They build narrative out of it. And so by doing that, even if they are trying to be as factual as possible, there's little elements of fiction that come in. But it's not the same fiction that you use when we are writing a story. Right?
I'm not saying about history, I'm saying about you. You want to understand the battle.
Yeah,
to understand the battle, you need in your mind to make up stories of different battles that resemble that one, but that differ in certain aspects with different outcomes. Mm-hmm. And this is how you really understand what this general sought to do and what he succeeded or failed to do.
Agreed. But you try to do that in a way that does not break consistency, right? So you are trying to fill the missing information in a way that is consistent, that does not contradict what you have observed. And I think there is an element here that is interesting, which has to do with memory. So, if you have like a machine that has like enough, let's suppose you have perfect memory of information that you have consumed in various ways, in texts, things that you observed, you have grounding, things like that. It's conceivable, but that you could have a machine that tries to fill those gaps in ways that are as faithful as possible to that we have observed. Maybe still bring some grains of fiction here and there, but with enough regularization that you are actually trying to build something as factual as humans can be.
Well, there is a bogus story about this. Funes de Memorios.
Yes, exactly. I was
And
thinking about this
Funes
story.
cannot unlearn things. He memorizes everything. And as a result, he's a complete idiot.
Yes. Yeah, but that's a little bit, that story is about a person that had an accident, right? And uses, let's say, one hot representations for everything, right? There is no abstract, he cannot abstract away anything. Yes, but that's okay. That's also an interesting point, but this was not where I wanted to get into.
No, I can see that.
I was interested in if you agree with this point that what moves from fiction to a factual machine is the ability of trying to build missing information in a way that does not contradict things that you have observed and that you have in your memory.
Well, I don't know how much you have in memory about historical battles. You haven't, I haven't been through any historical battle, but I read about them,
Yeah,
right?
That's also
So it's something that's already self-made up. So you try to be consistent with things that you read about historical battles in accounts that were probably fictional, most of them, or embellished.
Maybe some first principles about something that relate to what you think a battle is.
Common
You
sense.
don't need to exactly.
Yeah, you can try to use common sense, but
If I'm stuck somewhere, like if I have more people to fight, then I'll win, things like that, right?
yes, but this is what you use to understand the books that tell you about historical battles, fictional or real, and that make you decide whether they're actually good tools to try to complete, right?
Yeah.
Or maybe because you played as a kid to do war with other kids, and so you understand that hiding and surprising can be important, but you also read about the importance of surprise in battles. I never experienced it, right? But I read about it.
Yeah, I think it fits that we are filling in the missing pieces with, what we expect or some.
Yeah, but my point was that most of these missing pieces, they don't come from reality, they come from fiction.
Yeah.
When you want to teach something to
missing
children, you tell them a story, you don't tell them the truth.
Yeah. Missing pieces with missing pieces.
The first book about the object books where you have a drawing of something and the name below, the drawing of something, they're not realistic pictures. They're just symbolic view of what is a goat, what is a dog, what is a...
Okay, so I think we could be discussing forever, and I think maybe the Q&A took as long as the talk, but this was super interesting. Thanks a lot for the talk. And let's continue tomorrow. Don't forget again that tomorrow morning we're going to take a group picture in the break of the morning's talk. Enjoy. Thank you.